Welcome engineers. Today we are going to deal with the control system, that's DC traction analysis introduction majorly. So in DC tractions we have three types, that's series RL, series RC and series RLC, but today we are going to deal with two of them, the first two. So the curve of a traction analysis looks as the one given here, whereby we have a steady state and a transient state. So there are two major parts. We have transient response and the steady response. So a transient period is the period required for current and voltage to adjust themselves to the steady state. So that's the transient period where the curve is not stable yet, is rising to gain a stable or rather a steady state. So during the transient period, the mathematical expression of the current and voltage contain two significant terms, which are the transient and the steady state. So the transient terms are usually of short duration and damped out by certain damping factor which depend upon the circuit parameters. In general, when the switch is closed or open in a circuit, or if any voltage source is suddenly induced, transient conditions exist in the circuit. So in this given circuit here, where we have the switch there, we have VRV, the inductance. So this, let's look at the series RL circuit. So the given figure here shows a series RL circuit with a switch, resistor and inductor. So by KVL, finding the voltage, DC voltage of the circuit using the KVL rule, we have VDC is equals to VR plus VL. So whereby VR is the voltage resistance and the VL is the inductive voltage. So VR is equals to IR, that's what we know, and VL normally is equals to L di over dt. So here you'll have VR, solving this equation will have it as VDC is equals to VR plus VL is equals to IR plus L di dt. So L di dt plus IR is equals to VDC. So linear differential equation standard form of di over dt plus R over Li plus VDC over L. So particular solution of as VDC over
This initial condition is given by the voltage supply V over the resistance R, since at that particular moment, the capacitor is acting as a short circuit. This current equation, whose graphical representation is given by this, is applicable to any RC circuit with the capacitor having no initial charge. The time constant of a series RC circuit is the time when the capacitor is charged to 63.2% of its steady state value, and it is given by the formula R times C. For example, a series RC circuit is impressed with 12 volts DC. If the resistance is equal to 10 ohms and the capacitance is equal to 0.001 farad, assume no initial current at a conductor. Determine, letter A, the current at any time t. For letter B, calculate the current at time equal to 0.5 second. And for letter C, calculate the time when the current is equal to 0.75 ampere. Now for letter A, substitute the given values into our current equation so that we have 12 over 10 exponential negative t over 10 times 0.001. Our final answer will just be equal to 1.2 exponential negative 100t amperes. This equation is approximately represented by this graph. Now with this, we can see that as time increases, the current behaves in a declining fashion. The reason for this is that if you have a series RC circuit with a DC voltage source, once the switch is closed, eventually the capacitor will open. And at that particular moment, the current has already decayed to zero. Letter B, we want to calculate the value of the current at time equal to 0.5 second. And the answer is 2.31 times 10 to the negative 22. Practically speaking, this is already equivalent to 0 ampere. Letter C, we want to calculate the time when current is equal to 0.75 ampere. And from the same equation, we can find the value of time equal to 4.7 millisecond.